Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this comprehensive tutorial on Apache Flume. In this video, we'll explore what Apache Flume is, how it works, and why it's an essential tool in the big data ecosystem. Flume is designed to efficiently collect, aggregate, and move large amounts of log data from various sources to a centralized data store like Hadoop. Its distributed and fault-tolerant architecture makes it a reliable choice for real-time data ingestion. So why should you use Apache Flume? Flume excels at handling high-volume data streams, making it ideal for environments that generate massive amounts of log data. It ensures reliable data delivery through built-in fault tolerance mechanisms. Flume also supports a wide variety of data sources and sinks, making it highly flexible. Additionally, it integrates seamlessly with Hadoop and other big data tools, simplifying your data pipeline. Apache Flume's architecture is built around three core components: sources, channels, and sinks. Sources are responsible for ingesting data from various origins, such as web servers, social media, or IoT devices. Channels act as buffers, temporarily storing the data as it moves from sources to sinks. Sinks deliver the data to final destinations like HDFS, HBase, or Kafka. These components are organized into logical units called agents, which are the basic building blocks of Flume. An Apache Flume agent is a JVM process that hosts the core components: sources, channels, and sinks. Multiple agents can be connected to form a complex data flow, allowing for scalability and fault tolerance. Each component within an agent is configurable and replaceable, giving you the flexibility to tailor Flume to your specific needs. This modular design ensures that Flume can handle various data ingestion scenarios efficiently. Let's take a closer look at the architecture of Apache Flume. In this diagram, we see sources ingesting data from various origins. The data is then buffered in channels before being delivered to sinks, which send it to final destinations. Agents can be chained together to create more complex data flows, enabling scalable and fault-tolerant data ingestion across distributed systems. Sources are the entry points for data into the Flume system. They are responsible for ingesting data from various origins, such as web servers, social media, or IoT devices. Flume supports multiple input types including Avro, Thrift, and HTTP. Sources can also be configured to handle different data formats, making them highly versatile. Examples of sources include syslog, Twitter, and Netcat, each designed for specific data ingestion needs. Channels act as buffers between sources and sinks, temporarily storing data as it moves through the system. Flume supports both in-memory and file-based channels, each with its own trade-offs in terms of performance and reliability. Channels ensure data reliability and fault tolerance by persisting data until it's successfully delivered to the sink. They can be configured to meet different performance and reliability requirements, making Flume adaptable to various use cases. Sinks are responsible for delivering data to its final destinations. They support various output types including HDFS, Kafka, and HBase, making Flume highly versatile. Sinks can be configured to handle different data formats, ensuring compatibility with various storage systems. Examples of sinks include the HDFS sink, which writes data to Hadoop distributed file system, the Logger sink for debugging, and the Avro sink for sending data to another Flume agent. The workflow of Apache Flume is straightforward yet powerful. It begins with sources ingesting data from various origins. This data is then buffered in channels, ensuring reliability and fault tolerance. Finally, sinks deliver the data to its final destinations. Agents can be chained together to create more complex data flows, enabling scalable and fault-tolerant data ingestion across distributed systems. This diagram illustrates the step-by-step workflow of Apache Flume. First, sources ingest data from various origins. Second, channels buffer the data temporarily, ensuring reliability. Third, sinks deliver the data to final destinations like HDFS or Kafka. Finally, multiple agents can be chained together to handle complex data flows, providing scalability and fault tolerance across distributed systems. Let's look at a real-world use case: collecting web server logs using Apache Flume. In this scenario, Flume agents are deployed on multiple web servers to collect log data. The data is then streamed to Hadoop for analysis, enabling real-time monitoring and alerting. This setup can scale across distributed systems, ensuring that large volumes of log data are handled efficiently and reliably. This visualization shows how Apache Flume can be used to collect web server logs in a real-world scenario. Web servers generate log data, which is then collected by Flume agents. The data is buffered in channels and streamed to Hadoop for analysis. This setup enables real-time monitoring and alerting, providing valuable insights into web server performance and user behavior. Configuring a Flume agent involves defining sources, channels, and sinks in a configuration file. You'll specify the data flow between these components and set parameters for reliability and performance. It's important to test your configuration thoroughly before deploying it in a production environment. Proper configuration ensures that your Flume agent operates efficiently and reliably. Here's an example of a Flume configuration file. We define the source type and its parameters, such as the port number for an HTTP source. Next, we configure the channel type and its capacity, choosing between in-memory and file-based channels. Then, we set the sink type and its destination, such as an HDFS path. Finally, we link these components together to form a complete data flow. How does Apache Flume compare to similar tools like Kafka, Logstash, and Scoop? Flume is specifically designed for collecting and moving log data, while Kafka excels at handling real-time data streams. Flume is Hadoop native, making it a natural choice for Hadoop ecosystems, whereas Logstash is part of the Elk stack. Scoop, on the other hand, is designed for batch imports of structured data. The choice between these tools depends on your specific data ingestion needs. This chart compares the performance characteristics of Apache Flume with similar tools. Flume offers high reliability with moderate throughput, making it ideal for log data collection. Kafka provides high throughput and low latency, perfect for real-time data streams. Logstash offers flexible parsing capabilities, but with moderate performance. Scoop excels at high-speed batch imports, but is not suitable for streaming data. Understanding these differences helps you choose the right tool for your use case. Apache Flume offers several advantages that make it a popular choice for log data ingestion. It's highly reliable and fault-tolerant, ensuring that data is not lost during transmission. Its scalable and distributed architecture allows it to handle large volumes of data efficiently. Flume supports various data sources and sinks, making it versatile and adaptable. Additionally, it's easy to configure and extend, allowing you to customize it for your specific needs. While Apache Flume has many strengths, it also has some limitations. It's not suitable for complex data transformations, as it's primarily designed for data ingestion. Flume has limited support for batch processing, making it less ideal for certain use cases. For advanced analytics, you may need additional tools. Additionally, setting up Flume in large environments can be complex, requiring careful planning and configuration. To get the most out of Apache Flume, it's important to follow best practices. Use file channels for better reliability, especially in production environments. Monitor channel capacity to avoid bottlenecks and ensure smooth data flow. Configure multiple agents to achieve fault tolerance and high availability. Finally, regularly update and patch your Flume installations to benefit from the latest features and security fixes. Setting up Apache Flume in a cluster involves deploying agents on multiple nodes to ensure scalability and fault tolerance. Configure load balancing and failover mechanisms to distribute the workload and handle node failures. Use Zookeeper for coordination and configuration management. Finally, monitor the cluster's health and performance to ensure optimal operation and quick issue resolution. Security is a critical aspect of any data ingestion system. When using Apache Flume, enable SSL/TLS for data encryption to protect data in transit. Implement authentication and authorization mechanisms to control access to Flume components. Regularly audit configurations and access logs to detect any unauthorized activities. Additionally, implement network segmentation and firewalls to isolate Flume components and reduce the attack surface. Monitoring and troubleshooting are essential for maintaining a healthy Flume setup. Use JMX to monitor Flume metrics such as channel capacity and throughput. Regularly check logs for errors and warnings that may indicate issues. Monitor channel capacity to avoid bottlenecks and ensure smooth data flow. Use monitoring tools like Ganglia or Nagios to set up alerts and notifications for proactive issue resolution. Apache Flume plays a crucial role in the Hadoop ecosystem. It integrates seamlessly with HDFS and HBase, making it easy to store and manage large volumes of log data. Flume also works with other Hadoop tools like Hive and Pig, enabling advanced analytics and data processing. As part of the broader big data ecosystem, Flume supports data ingestion for analytics and machine learning applications, providing a reliable foundation for data-driven insights. Looking ahead, Apache Flume will continue to evolve to meet the changing needs of the big data landscape. It will maintain strong support for Hadoop ecosystems, while also integrating with cloud-based storage solutions. Expect enhanced security and monitoring features to address modern security challenges. Additionally, Flume may adopt modern streaming architectures to stay competitive with newer data ingestion tools. If you're interested in learning more about Apache Flume, there are plenty of resources available. Start with the official Apache Flume documentation for comprehensive guides and references. Online tutorials and courses can provide structured learning paths. Engage with the community through forums and mailing lists to get help and share knowledge. Finally, hands-on practice with sandbox environments will give you real-world experience with Flume configurations and use cases. Let's get hands-on with Apache Flume by setting up a simple agent. First, install Flume on your local machine. Next, create a configuration file that defines a basic agent with a source, channel, and sink. Start the agent and monitor its operation to ensure everything is working correctly. Finally, test data ingestion by sending sample logs through the agent and verifying that they reach the destination. When configuring Apache Flume, there are some common mistakes to avoid. Incorrect channel capacity settings can lead to bottlenecks or memory issues. Mismatched source and sink configurations can cause data loss or processing errors. Neglecting to monitor channel throughput can result in unnoticed performance degradation. Overlooking security configurations can expose your system to vulnerabilities. Being aware of these pitfalls will help you set up a more robust and secure Flume environment. In production environments, Apache Flume requires careful planning and management. Deploy Flume in high-availability configurations to ensure continuous operation. Use monitoring and alerting tools to track performance and detect issues early. Implement backup and recovery strategies to protect against data loss. Regular performance tuning and optimization will help maintain efficient data ingestion and processing. Let's explore a case study of Apache Flume in an e-commerce environment. In this scenario, Flume is used to collect user activity logs from web servers. These logs are streamed to Hadoop for analysis, enabling real-time personalization and recommendations. The system is designed to scale and handle peak traffic periods, ensuring that user data is captured and processed efficiently, even during high-demand events like flash sales. Apache Flume can be integrated with Apache Kafka to create powerful data pipelines. By using Kafka as a sink, Flume can stream data to Kafka topics in real time. This combination leverages Flume's reliability for data ingestion and Kafka's scalability for data streaming. Together, they support complex data pipelines and enable advanced analytics and real-time processing scenarios. When deciding between Apache Flume and Apache Kafka, consider your specific use case. Use Flume when you need reliable log data ingestion with built-in fault tolerance. Kafka is better suited for high-throughput real-time data streams. Flume is Hadoop native, making it ideal for Hadoop ecosystems, while Kafka is stream native, perfect for real-time processing. Your choice should be based on the nature of your data sources and destinations. Apache Flume offers several advanced features that enhance its flexibility and power. Interceptors allow you to enrich or filter data as it flows through the system. Channel selectors enable intelligent routing of data to different channels based on criteria. Sync groups provide load balancing and failover capabilities for improved reliability. Additionally, you can develop custom components to meet specific use cases, making Flume highly adaptable to your needs. Flume interceptors are powerful tools that modify or filter events as they flow through the system. Common interceptor types include timestamp, which adds a timestamp to events, host, which adds host information, static, which adds static headers, and regex, which filters events based on regular expressions. Interceptors can be chained together for complex processing workflows, enabling data enrichment and validation before events reach their final destination. Channel selectors in Apache Flume determine how events are routed to channels. The replicating selector sends events to all configured channels, ensuring redundancy. The multiplexing selector routes events to specific channels based on event headers, enabling targeted data flow. You can also create custom selectors for advanced routing logic. These selectors provide flexible data flow management, allowing you to optimize your Flume setup for different scenarios. Sync groups in Apache Flume allow you to group multiple syncs together for load balancing and failover. This setup improves reliability by ensuring that if one sync fails, others can take over. Sync groups can include different sync types, providing flexibility in how data is delivered to destinations. By using sync groups, you can achieve better performance and high availability in your Flume data pipelines. Apache Flume's extensibility allows you to develop custom components tailored to your specific needs. You can create custom sources to ingest data from unique origins, custom channels for specialized buffering, and custom syncs to deliver data to proprietary systems. This flexibility enables you to extend Flume for specific data formats or protocols, integrate with proprietary systems, and enhance functionality with custom logic, making Flume a truly adaptable data ingestion solution. In conclusion, Apache Flume is a powerful and reliable tool for log data ingestion in big data environments. By understanding its architecture and components, you can leverage Flume to build efficient data pipelines. Exploring real-world use cases and integrations will help you see its practical applications. Finally, hands-on practice with configurations and setups will solidify your knowledge and skills. We hope this tutorial has provided you with a comprehensive understanding of Apache Flume and inspired you to explore it further. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.